Hello, everybody. It's a real pleasure to introduce today's speaker, John Percival. John earned his bachelor's from Concordia University and his master's and PhD from Queen's University, and he spent his career shaping how we understand the Archean crust of Canada. He began his work with the Geological Survey of Canada, leading regional mapping projects in remote and unexplored regions of northern Manitoba, Ontario, and Quebec. Through that work, John helped establish the modern view of the Archean Superior Province as a collage of continental and oceanic terrains assembled around 2.7 billion years ago through processes similar to those operating today. Many of you will also know John for his central role in Lithoprobe, Canada's flagship multidisciplinary geoscience program. From leading the Kapuskasing deep crustal transect to spearheading the synthesis of 10 lithoprobe transects across the country, his work culminated in the landmark volume Tectonic Styles in Canada, the Lithoprobe Perspective. Over the course of his career, John has authored more than 300 journal articles, reports, maps, and book chapters. He also served as an adjunct professor, teaching and supervising undergraduate and graduate students on multiple editorial boards and contributing extensively to national and international geoscience communities. In addition to his research career, John has played a major leadership role in Canadian public geoscience, including managing the Northern Geoscience programs in support of Canada's Northern Development Strategy. His contributions have widely recognized, including being named two-time Howard Street Robinson Distinguished Lecturer of the Geological Association of Canada and receiving the Gold Medal of Professional Institute of Public Service of Canada. John continues to be actively engaged in research and advisory roles, including service with the Canadian Nuclear Safety Commission and Laurentian University's Metal Earth Program. We're very excited to have him with us today. Please join me in welcoming John. Please take it away.
Thank you, James. This project is a new direction for me, working in Paleoproterozoic rocks, relatively low grade, from the Rae Province. And so I was on a steep learning curve, and I'd like to acknowledge the contributions of my co-authors here, and I'm accepting full responsibility for any misinterpretation of their results. There we go. So I'm talking about a spherule bed within a Paleoproterozoic sequence about 2.1 billion years old. This is the discovery outcrop that we came across in 2012 as part of a reconnaissance study of this area. We were looking for areas that required upgrading of the geological database, and the Montresor region hadn't been mapped since the 1980s and looked ripe for new interpretations. So at the time, I had no idea what these features were, and so collected a sample. And I'd never come across features like this before, and so I was curious about what they were, but it kind of went on the back burner because there were more pressing geological issues to resolve. About this time, there was some attention dedicated to the study of spherules, a special issue of Elements in 2012, and an excellent book on distal impact ejecta layers published in 2013. So when you come across one of these, which are quite rare in the geological record, only about 28 are known from the whole geological record since about 3.5 billion years ago, you're faced with questions like, where did these come from? What's their age? Where's the crater? What kind of rocks were involved in this? And were there any climatic, biotic consequences of this kind of thing? And so we parked these questions for the time being because there was no geological context for these at the time. The previous geological map showed the area containing the spherule bed as being part of the Archean basement to relatively simple Paleoproterozoic synform of sedimentary rocks known as the Montresor belt. These rocks shown here in M are part of a widespread cover sequence on the Rae known as the Rae cover sequence, preserved as erosional remnants, and may correlate with a broader package of sedimentary rocks in southern Baffin Island, known to be Paleoproterozoic, but not very well constrained in terms of age. So this shows the results of our geological work in the region involving a new interpretation of the Montresor group, subdivision into a lower Montresor group that's thrust imbricated with Archean basement, consists of quartz-rich rocks shown in yellow, some dirtier sediments in green, and that's the bed containing the spherule bed, and then a younger wacky Arcos carbonate sequence that we named the upper Montresor group, the distinction being that these rocks are not imbricated with the basement, whereas the lower Montresor groups, including carbonate, shown in blue, are imbricated with Archean rocks. And the basis of that interpretation is geochronology. There are detrital zircons in these quartz-rich rocks, and they show a bimodal distribution of Archean and Paleoproterozoic zircons, quite a notable cluster here that centers at around 2190 million years old. And so these rocks are deposited somewhat after 2190. And the lower limit is provided by a boudinaged gabbro sill within this sequence. And there are both inherited and igneous zircons within this gabbro. The igneous zircons provide an age of 2045 million years, but with relatively large uncertainty. So we're within a bracket between about 2.9 and 2.05 billion years for deposition of these rocks. The younger group, the Arcos carbonate sequence, has detrital zircons as well, and they indicate a maximum age of 1924 plus or minus 6. I won't be talking further about those rocks, but I'll be focusing now on the rocks containing the spherule bed. So this shows the revised tectonostratigraphy for the Montresor belt, the lower belt having these constraints between 2.19 and 2.045, and the younger rocks with that. And they're all deformed and metamorphosed by the trans-Hudson origin that lasted from about 1.9 to 1.8 billion years ago. And the reason that age bracket is significant is because it coincides with some major events in Earth history, including the end of the Lomagundi carbon isotopic exchange excursion, at the end of the Great Oxidation Event. And the constraints on that are also somewhat loose, but include this bracket that we have for the spherule bed in the Montresor group, which is shown in the red. And this is a summary of estimates as of 2013 for the age of the Lomagundi carbon isotopic excursion. So this could be significant. So that gives reason to go back and have a close look at the spherule bed. And so the reason for this collapse in organic productivity is likely related to exhaustion of resources in the ocean. So the nutrient supply was limited by limited tectonic activity and continental uplift, erosion, and likely the supply of nutrients in the oceans just ran out and the organic matter died off. However, that scenario doesn't include the presence of a large impact during that window. So the question is, could an impact have influenced this decline in bioproductivity in that end of Lomagundi period? So that's why this work could be significant. Let's have a closer look at the spherule bed now. This shows the extent. It's got some kind of zonation, bedding possibly, that shows distribution of spherules that range from about 1 millimeter in size down to about 100 microns. We're looking here at the perpendicular defoliation surface, so there's a bit of exaggeration owing to the flattening caused by the Trans-Hudson deformation at 1.85. So if you look perpendicular to this surface, you see that there's a preferred orientation to the spherules. They're pancake shaped with about 2 to 3 to 1 exaggeration, and that translates to about a 1.4 exaggeration factor versus the original spherical shape. And having a closer look, these spherules are cryptocrystalline, quite fine grained in size. You need an SEM to identify the minerals and look at the zonation. They are zoned mineralogically from an assemblage that includes phengite in the cores to an assemblage that's dominated by prehnite in the rim, sort of the mantles. And then the matrix consists of quartz, chlorite, K-feldspar, a little bit of biotite, and graphite. And using Theriac domino phase assemblage techniques, using the observed bulk compositions of these zones, you can create a phase diagram for the stable assemblage that includes chlorite, phengite, and prehnite that defines temperatures to below about 300 degrees and pressures below about 3 kilobars. And I'm going to take a pause here for a moment. Phengite and prehnite are very similar sounding minerals, but they're quite different in their significance. So prehnite is a phyllosilicate, calcium aluminum silicate with some water. It's a low pressure temperature mineral that occurs in subgreenschist facies assemblages. You're probably all familiar with prehnite pompelliite facies. Prehnite chlorite assemblages occur below that in PT space, so very low metamorphic conditions. Whereas phengite is also a phyllosilicate dominated by potassium, and it's distinguished from ordinary muscovite by having higher silica and magnesium, and that difference is the result of a pressure-sensitive substitution of silica plus magnesium for 2 aluminums, so you can create a more dense structure using silica and magnesium in the structure versus 2 aluminum atoms. And phengite normally occurs in eclogites and ultra-high pressure rocks, as well as in rocks of unusual bulk composition. So we'll have an even closer look now at the core characteristics where phengite occurs. And within these cores, you can see at quite small scale, the mineral assemblage quartz, a little bit of titanite, some prehnite, and phengite in here, and then ultrafine patches. And we've zoomed in even closer to identify the minerals within these ultrafine patches, and they pretty much mimic what's there in the surrounding material. with the exception of calcite being additional phase, but there's calcite, prehnite, phengite, chlorite, and I'll just draw your attention to the phengite, which has an additional unusual characteristic that it's only semi-crystalline. And I'll go into that in more detail after talking about the bulk composition of the phengite. So this is a compositional diagram plotting magnesium versus silica. All the red points are data points for phengite from the spherules using different analytical techniques. So we've got some microprobe analyses, some SEM analyses, TEM and laser ablation analyses, but they all plot at quite high silica levels. And the comparative data on here come from some experiments in 2010 that synthesized phengite at different pressures. So these are 2.3 gigapascal compositions all the way up to 8 gigapascals. That's 80 kilobars, corresponding to depths of around 250 kilometers or so. And so these compositions, a lot of them correspond to some of the higher pressure experimental compositions. That arrow is the alpine UHP decompression path for comparison. And then down here, we've got normal regional metamorphic muscovite from the area. And this point is a neoblast of muscovite from within the same bulk composition in the spherules, and I'll point that out in a moment. This EBSD image highlights the amorphous or poorly crystalline nature of the phengite, which is shown in black. This is a band contrast image, and the low band contrast indicates low crystallinity. There are no Kikuchi patterns from these areas, whereas all the other minerals that are part of the regional metamorphic assemblage, prehnite, quartz, etc., and that's a muscovite neoblast there that I showed you in the last diagram, is crystalline, whereas the rest of this material is poorly crystalline, to say the minimum. And if you have a real close look with the SEM, you can see that the phengite masses consist of very tiny particles. This triangular shaped particle is actually an aggregate of smaller particles. It's only about 300 nanometers in size, but you can see there's one particle there, another particle there, another particle there that make up this aggregate. So the size of the individual phengite particles is in the sub-micron range, and that's extremely fine. For example, forest fire smoke, the particle size is in the 0.1 to 2.5 micron range, so the same size range, which is very good for light scattering and reflection of light and darkness. So I had mentioned poorly crystalline structure. This kind of resolves the crystallinity and the nature of the poor crystallinity. This is a TEM dark field image. Normally on selected area diffraction patterns, minerals provide a diffraction pattern. You can measure the spacing of the points, and there's a good encyclopedia so you can identify minerals. However, these phengite particles produce diffraction halos, which indicate either amorphous or nanocrystalline nature. And you can query these diffraction halos to show the nature of the diffractions coming from this. So this is halo C, and what you see in this very detailed image is a pattern of dark bands here, which are amorphous, and the light areas are crystalline areas. And so you can see kind of a crisscrossing pattern of amorphous features and islands of crystalline material left between the amorphous bands. So I think this is analogous to shock features at somewhat larger scale. For example, in quartz, you can see this is on a 0.5 micron scale. So these amorphous bands are a couple of 100 nanometers in size, whereas these are only 1 or 2 nanometers in size. But you can see this is qualitatively a similar pattern at a larger scale caused by shock metamorphism in an impact crater. To cause amorphization of muscovite, experiments show that you need pressures around 18 gigapascals. So pretty much the only process you can appeal to get pressures of that magnitude are shock features associated with craters. So let's do a quick summary of these spherule characteristics. Their pre-deformation size is about 700 microns. They're mineralogically zoned and chemically zoned from potassium-rich cores to calcium-rich rims, metamorphosed to subgreenceous facies. There's relic phengite in the cores. Those particles are submicrons in scale. In detail, they have an amorphous nanocrystalline structure. They're not in compositional equilibrium at the regional metamorphic conditions, and it looks like they could have survived the impact as just shocked dust particles. Dust is a fairly common product of impacts. Part of the impact plume is vapor. The top part here reaches extreme pressures in 100 gigapascal range. Most of that material is vaporized and comes out. But below that, at less shock pressures, this material is excavated as dust particles. And similarly, the projectile, much of it is vaporized depending on the angle of impact. So vertical impact produces much more vaporization, up to 50%, whereas lower angle impacts produce no vaporization. But the remainder of this material is dust-sized particles. So dust is a major feature of impacts. And this has been recognized for the Chicxulub-related impact site, probably the best studied impact system in the world. And a lot of papers have now considered that dust was a major factor in the demise of the dinosaurs, among other things. But fine silicate dust is a major player that creates sustained impact winters. And the particles within that dust are down to nanometers in size. These nanoparticles of the impactor were detected using synchrotron techniques. So fine particles, a lot of dust, long residence time in the atmosphere, and severe environmental consequences for living things. I'm just taking a short break here. That's a lot of information. I'll let you take a few minutes to process it by giving you some scenery shots. And it's kind of daunting when you see the airplane leaving your camp there for a couple of weeks, and not alone. We sometimes had visitors. This is a caribou herd migrating through our camp. And it can be very pleasant in the summer when it's warm and there aren't too many bugs around. You can go walking with the locals. So back to science. One of the things we want to know about the impact process here is, what is its age? What are the crater materials? Where could that constrain where the crater could be? I neglected to mention that there's no known crater of this age. There's an older one, Yarrabubba in Australia, and a younger one, Vredefort in South Africa. But the age constraints of those are quite tight, and this falls between those, and so there's no known crater. So we're left looking for clues within the spherules. There are some small sparse zircons within the spherules. They're complex, and they could provide clues to the age of the basement, maybe even the age of the impact, but analytically challenging because of their size and complexity. Geochemistry can be an asset. We can determine bulk spherule compositions, remembering that the bulk composition is a mixture of target and impactor materials, but there are microanalytical tools available to give us that information, although the interpretation is challenging because of this mixing situation, not to mention mixing of crustal materials, basement, and potential cover rocks. But let's proceed with these. I mentioned complexity in the zircons. They're quite sparse and small. So in the 5 to 20 micron size range, most of them. And they're multi-components. Many of them have featureless internal xenocrysts. They're quite metamiced. Some of the metamiced zones contain galena spherules. And then there are metamorphic rims around, many of them variably developed. So we need special tools to look at features of this size. This whole zircon is only 5 microns wide, so individual zones are only a couple of microns in size. For comparison, shrimp spots are usually about 25 microns, so you could not distinguish individual zones. So we turn to the UCLA ion probe with an RF source, which can get spot sizes down in the low micron range. And this shows an attempt to date this zircon. That's the pit from the ion probe. And as you can see, it did mainly sample this zone here, but it also acquired information from the metamiced zone, including the galena here. And as a result of that, the age was relatively imprecise, with a large uncertainty here, about 50 million years. And that's characteristic of all the zircons we tried to date. There were about a dozen, and we got ages ranging from about 2.8 to around 2.1, but not really very definitive, and nothing discernibly related to the impact. So that was a bit of a dead end. Geochemical constraints are more profitable, perhaps. The ultimate goal here is to reconstruct the source terrain characteristics. And so we looked at bulk compositions, analyzed for 10 major 32 trace elements. But to assess the reliability of those, we need to first look at alteration. Many spherules are altered either through seawater interaction, matrix interaction, and in our case, metamorphic processes. So we had to look in some detail using laser ablation maps to assess the effects of alteration before being able to use the bulk compositions in any meaningful way. So look at some major elements first: silica, aluminum, calcium, and potassium. Together, these represent about 90% of the mass of the rock. And you can see there's an obvious chemical zonation here with the calcium-rich mantle and potassium-rich core. So in terms of potential alteration, that calcium-rich mantle could be the product of diagenetic carbonate replacement in a reaction something like this. So original calcite plus lomantite, a zeolite, could have been metamorphosed to prehnite quartz with loss of volatiles. However, there's very low calcium in the matrix. It's a mudstone, quartz chloride, K-feldspar, so no calcite there. But it's still possible that there could have been calcium introduction from seawater during the descent in the water of the spherules to the seabed. And so you would predict, if that was the case, that the trace elements in seawater should be associated with the calcium. So there should be a relationship between calcium, magnesium, strontium, barium. And we can look at that using the maps. So there's the calcium-rich mantle, and you can see that there's not much association with magnesium, definitely no association with strontium or barium here. So that doesn't look like a very strong argument for carbonate infiltration. On the other hand, there is quite a strong correlation, spatial correlation with zirconium and europium. So that could signify a higher temperature process, possibly something primary rather than a carbonate replacement process. And then if we look at large ion lithophile elements, which are quite susceptible to mobility during any kind of secondary alteration process associated with fluids, you can see that these things which are quite mobile, like lithium, rubidium, strontium, those patterns, kind of that egg-shaped pattern here, correspond fairly well with high field strength elements like vanadium, niobium, tungsten, and you can include scandium and other high field strength elements in that pattern. So it's likely that these elements probably weren't strongly mobilized during the alteration process. They probably reflect something close to the original bulk composition. These are bulk compositions plotted in terms of potassium, magnesium, and calcium. This is taken from a spherule composition comparative paper. And so I've used various comparative data here: upper continental crust, bulk continental crust, ocean island basalt, lower continental crust. These are anorthosites in here. And the squares are some comparative spherule data from Devonian age spherules. Also plotted phengite on here as a possible end member. And what you can see here in the spherule compositional range is a potential mixture of potassic and calcic end members, which is not surprising considering the observed zonation. So let's turn to trace elements, and specifically high field strength elements. These are known to be relatively immobile during secondary alteration and metamorphic processes, and so tend to be fairly robust in interpretation of these kind of rocks. So I'm focusing here on niobium tantalum ratio here. And this pattern shows the distribution of Montresor spherules in terms of their niobium tantalum ratio and niobium content. 38 parts per million niobium is quite high. Average crust has about 12. Archean TTG, similar. But most other rock types have very low niobium tantalum ratios in this range, below chondrite. The only rock type that squeaks up into here is Archean TTG, but these are at very low niobium levels. So these spherules are difficult to explain in terms of their high field strength element contents and ratios. When we can look at niobium tantalum in the geochemical maps, and this shows all 5 spherules that were mapped in detail. And you can see that niobium tantalum appears to be a kind of an intrinsic property of the spherules. It's difficult to make a case that this has been leaked in from the matrix. More likely it's there as an original characteristic that hasn't escaped during alteration processes. Similarly, zirconium hafnium the ratios are unlike most terrestrial materials. And I've also included here other objects in the solar system, the moon, Mars, that's an asteroid, Vesta. So there's really no comparative material that we can point to that could be the contributor for these compositions. And we've looked at the alteration possibilities, and that doesn't seem very likely. So to explain enrichment in high field strength elements, as well as these unusual element ratios, you need to look at highly unusual rock types, including rare metal deposits. And I've plotted a few of these on this diagram. This shows niobium lanthanum. So this would be the big trough on a spider diagram for all of these rocks with negative niobium relative to lanthanum. Almost all of the spherules have positive niobium relative to lanthanum. And there are a few rocks you can identify with that high niobium lanthanum ratio. One is some unusual carbonatites. These would be rare metal deposits mined for niobium and light rare earths. But they also have very high lanthanum ytterbium ratios. There's a rare rock type called absarokite that occurs in some rare back arc settings. There's a peralkaline granite in Russia, a small rare metal deposit that's in here. And that's Ocean Island basalt. But all of these are down at this end of the compositional spectrum. And there's nothing up here that could be a mixing end member to produce this array of compositions. So we're left with a collection of unusual observations here. Dust-sized particles of structurally damaged high silica phengite. That's normally a trace mineral in ultra-high pressure terrains. It's certainly not widespread at Earth's surface. The bulk compositions have high field strength contents. You kind of need some kind of a rare metal deposit contributor, but as the name implies, these deposits are very rare. and then superchondritic high field strength element ratios for which there are no viable analogs. So I've had to consider the possibility that the impactor was exotic to the solar system, but you get into the realm of untestable hypotheses here because there's no comparative material. There are no established criteria for what could constitute material from outside the solar system. And you're left with having to consider the probability of that event occurring, and then the plausibility of different processes on exoplanets. So talking about the probability, that was extremely low prior to 17 because there were no examples known of extra solar material. Then in 2017, astronomers discovered Oumuamua's passage through the solar system. It came and went fairly quickly in a trajectory and at a velocity that didn't coincide with anything from the solar system. So this was a first example documented of something from outside the solar system that came through, didn't hit anything, went back out the other side. And then in 2019, a second object was identified, comet Borisov, and same situation. Velocity was too high, trajectory unusual, and it came and went through the solar system. So at that point, astronomers redid the probabilistic considerations, and based on the observation window, which was quite limited, had only been observing for a couple of years, and they detected one of these interstellar interlopers. So based on that, they predicted that one of these extrasolar objects could hit the Earth every 30 million years. And there could be 6,000 of these asteroids within the solar system at any time, trapped in orbit over time. And using the statistics, they predicted a maximum impactor size of about 5 kilometers and a rate of impacts of 1 per 10 to 100 million years. And then more recently, the frequency of extrasolar bodies greater than 100 meters impacting the Earth. So 1 per every couple 100 million years. So probabilistically, this is not an unusual occurrence over the lifespan of the Earth. And what about plausibility? If you're talking about exoplanets, you're dealing with mainly similar rocky compositions to our rocky planets, so Earth, Mars, etc. And that's just a cosmochemical fact that there shouldn't be major differences in bulk composition, so similar distribution of major elements, trace elements. However, there could be unrecognized conditions and processes on these bodies. This is just one example. There are several exoplanets that are tidally locked, so relatively close to their stars, and they don't rotate. So there's a day side, a permanent day side, and a permanent night side. The temperatures on the day side are supersolidus with respect to these materials. And so there are probably lava lakes on the surface of this planet in this area, quite deep lakes. And these perpetual magma oceans have the potential to produce geochemical fractionation unlike anything that we have in our solar system. And so that would be one way of fractionating niobium from tantalum that we don't have a way of doing on our in our solar system through normal Earth processes. So to sum up, 1.777 centimeter spherule bed. Within this age bracket, there are preserved ultrafine dust particles in the cores, consistent with a decades-long impact winter. That age bracket overlaps some major events in Earth history. The spherule map suggests that the chemical zonation is preserved and preserved original feature. There are minor alteration effects, and the bulk composition resembles continental crust, but there are some unexplained anomalies in the trace element signatures, and we're considering that the impactor could have been exotic to the solar system. And with that, I'll thank you for your attention and answer any questions either now or if you want to email me. That's my email address if you've got anything more specific you'd like to talk about.
All right, thank you very much. If you want to ask a question, feel free to type it into the chat or use the raise your hand feature. And the first hand that I'm seeing is Greg, so feel free to go ahead.
John, that was a blast. What a lovely lot of data. I really enjoyed that a lot. But it occurred to me there may be another analog on Earth that you might want to consider, and that is soil. Maybe it impacted one of those Precambrian paleosols. Have you tried comparing those? And the reason I say this is because of two things. When you showed the slide, it looked like the spherules were matrix supported. If they had landed in any amount of water at all those spherules would have gone to the bottom, but they didn't. They may have landed on land. And the other thing, sphengite, it's a form of selatonite. It's an extremely common metamorphic, shallow metamorphic diagenetic alteration of rhyodacite tuff paleosols in Oregon. It gives them that really weird green color that doesn't belong in nature. So I'm wondering if it might not be productive to take a look at some of the old Precambrian paleosol papers by Dick Holland and others, the big thick regolith papers, and compare them to your spherule compositions.
I haven't looked at those. I know that niobium and tantalum don't fractionate in superficial environments, so that's not a way of resolving that problem. I considered the possibility of the phengite being diagenetic, which I think is very reasonable. However, the amorphous bands at extremely fine scale are not consistent with that. If you have diagenetic formation, that's a fully crystalline material that forms in place, and you can't these what I think are shock features through that process.
Yeah,
but I'll look into the paleosol.
You're still speaking, John? Oh, yeah. So the amorphous nature, that is a characteristic feature of volcanic sols called andersols. And it forms during sol formation from volcanic glass. The glass is amorphous to start with, and then the alteration product in the soil becomes amorphous material, amorgolite, basically. Very similar to what you've got. But you can also form amorphous material by the glass reaction from impact as well. and both, I think, can make that. I don't think that's a mystery. Zircon enrichment is definitely a feature of soil formation, particularly deep soil formation. I'm not sure about niobium to tantalum. I'd have to look up that one, but you may be right. That's not going to explain that. But wow, so interesting. Fascinating example.
All right. Don Davis, would you like to go?
Yeah, okay. Thanks, John, for a very stimulating talk. I just have a couple of short questions, not as expert as the last ones. One is the two dyke zircons, zircons that you dated in the boudinaged mafic dyke. How are you sure that they're actually in the dyke rather than xenocrysts?
There are xenocrysts as well.
Yes.
Mike Hamilton had a look at them and dated them. They morphologically they're different. They're small. They look like they've got some kind of igneous zonation in them.
Oh, they do.
So he interpreted them as igneous, but
well, they are igneous, but the question is whether or not they're from another rock or whether they're from the mafic rock that they're hosted in. One way to tell is that usually gabbro zircons have relatively high thorium over uranium ratios above 1, which you hardly ever see. The other thing is that they're not usually oscillatory zoned, which is developed in silica-rich magmas. So if they have they should have broad zonation and have relatively high thorium over uranium to be sure. But I'm just curious because obviously that's an important point for setting a minimum age on the impact. The other thing is I wonder if the difference between the high niobium and tantalum and zirconium over hafnium ratios might be related to the difference in volatility. Both niobium and tantalum are quite refractory, but tantalum and hafnium are a bit more refractory than the other two elements. So that's just a suggestion. I don't know whether you considered it.
I did consider that, and I think the main argument is that these were not vapor materials; they were crystalline materials. So at least the fangite with the shock textures in didn't go through a vapor phase. So there isn't the potential for that vapor fractionation, which you would see if these were condensed glass spherules.
Yes, yeah.
But the point about the zircons is very important. If they are inherited, then the minimum age could be
it's a maximum age.
Younger.
Yes.
Right.
Yeah. Okay. The third point is the question of whether or not the meteorite might have been from an exotic source. Well, if that were the case, I would expect to see very large isotopic anomalies in everything, because there's no reason to expect that another solar system would have condensed with the same ratios of isotopes that we see commonly. So that would be the first thing to check if you want to kind of rule that out.
Agreed. The question is, would the volume of the impact material be discernible? That the difference in isotopic composition is diluted because you're mixing like 95% crustal material with it. So it wouldn't be such a striking anomaly unless you can find particles from the impactor that you could zoom in on.
Or the most impactor enriched material that you could find. Yeah.
Right.
Okay, great. Thanks very much then.
Thanks.
All right. Daryl, would you like to go?
Yeah, I'm amazed you got so much information out of such a little piece of rock that most of us would probably have walked over. To ask you a totally left field question, can you get any indication of the size of the impactor from your geochemical data?
No. um, I'm based on the Chicxulub examples. There's really no way of estimating the relative size or the relative contribution of impactor in different locations around the world. You get different estimates depending on where you are. So there's probably some kind of unmixing of the two components the further you get away from the impact site. And so all the estimates, even for Chicxulub, are quite spread out. And so from one example, I don't think you can make that estimate.
Okay.
Okay. Maybe I can ask John two questions. First, kind of just basic. You mentioned that the lower part is imbricated with a basement, and upper part, it seems like you implying it's in a thrust, was thrusted over lower part of Montresor, imbricated with basement. Is it correct?
Actually, I think it's extensional. The contact between those two units is structural, and I've made the interpretation that it's an extensional structure rather than a thrust structure.
Okay.
Not based on kinematic information, based more on differences in metamorphic grade between the lower Montresor and the upper Montresor.
So do you envision some tectonic event between lower and upper Montresor, or just large scale displacement, like why we have different metamorphic grade and imbrication versus no imbrication?
I think the imbrication probably occurred in the lower part of the sequence, like in the Amer group, and the thrusts had limited penetration into the lower Montresor, and didn't extend through into the upper Montresor stratigraphy. And then during some kind of orogenic collapse event, the upper Montresor was in extensional contact with the lower part. It's interpretation, but I'm sure there's other interpretations possible.
Thank you. And the second question, it's out of my field, but you mentioned that niobium tantalum fractionation, this niobium tantalum high ratios common to carbonatites, which kind of made me think around 2060, 2065. It's the time of large igneous provinces like Bushveld. And it's also time when carbonatites were formed like Pilabora. And so I'm wondering if it could be some volcanic ashes related to carbonatite volcanism. But I guess the pressure estimates would not be consistent with it. So do you have any thoughts on it?
Also, phengite is not a characteristic mineral of carbonatites. The carbonatite I showed on that diagram is a rare carbonatite. They don't all have that high ratio. Also, there's very little carbonate in the spherules, a tiny little bit in the cores, but it's certainly not a common mineral. So you'd have to do some major modifications to the bulk composition. And then you can't explain the shock features as well through normal volcanism.
Okay, Thank you.
All right. Thank you very much. Are there any other questions out there?
Actually, we have a question from Huang. Maybe you can ask yourself, but it's actually switching topic to, I guess, what John did before this project. And he asked, what's the protoliths of the 2660 million year mafic granulite of the Kapuskasing schizol. Sorry, it's kind of out of the stock, but that's the question.
Well, if Mr. Chair will allow me to divert from the subject matter. So those mafic rocks were probably metabasalts. The zircons in there are metamorphic, and there are some metasediments as well as those mafic rocks that look like an older supercrustal sequence that was probably deposited around 2750 and then metamorphosed at 2660 million years.
Thank you. And Juan, if you have more questions, I'm sure John would be happy to answer your email. Paul?
Yeah, not a question. I just want to congratulate John for aggressively following up an interesting observation in the field.
Thanks, Paul. As I said, I had no idea what these features were when I picked up the rock. I just picked it up because I was curious, and it turned out to be interesting.
Yep. That's the point. Curiosity.
All right. Thank you very much, John. It was a wonderful talk.
And next week we will have, we're still waiting for abstract, but we will have a talk from a petrologist, working experimental petrologist, but it will have bearing on estimates of mantle redox for Precambrian. So it's a more petrological talk, but kind of should be interesting.
Thanks, everyone.
Mm-hmm.
Thanks, John.